Hey friends, welcome to the YouTube channel all about electronics. So in the previous video, we have seen the condition for the stability in the feedback amplifier and we understood the concept of the gain crossover frequency and the phase crossover frequency. So similarly, in this video, we will understand the concept of the phase margin and we will also see that using the frequency compensation technique, how to improve the phase margin of the feedback amplifier. So if you recall the previous video, then we have seen that typically in the feedback amplifier, this open loop gain is the function of the frequency. And we have also seen that typically this feedback network is the passive network. And because of that, it is independent of the frequency. So in such case, this closed loop gain can be given as A divided by 1 plus A beta, where this A is the function of the frequency. So we have seen that whenever this A beta is greater than 1 and the phase of the A beta is equal to minus 180 degree, then this feedback amplifier will become unstable. And then we have also seen that this Bode plot is one of the way to finding the stability of the feedback amplifier. So then after we have proved that when the feedback amplifier has a one pole or the two poles, then the response of the feedback amplifier will be inherently stable. But when it has a three poles, then it is quite possible that the system might become unstable. And it can happen whenever this gain crossover frequency is more than the phase crossover frequency. So the gain crossover frequency is the frequency at which the magnitude plot crosses the 0 dB. Or we can say that when the magnitude will become 1. So in this case, at the gain crossover frequency if we see, then the phase is less than minus 180 degree. So here, the issue of the instability will occur. Because in the stable feedback amplifier, when the phase reaches the minus 180 degree, at that time, the amplitude should be less than 1. But in this case, that is not satisfied. So here, the frequency at which this phase reaches the minus 180 degree is known as the phase crossover frequency. So for stability, this phase crossover frequency should arrive after the gain crossover frequency. Or in other words, this gain crossover frequency should be less than the phase crossover frequency. So that when the gain crosses the 0 dB, at that time, this phase is more than minus 180 degree and hence the issue of the instability won't occur. So now the question is how these two frequencies should be apart from each other. So here first let us see the two cases. So in the one case, this gain crossover frequency is same as the phase crossover frequency. And in the second case, this gain crossover frequency is slightly less than the phase crossover frequency. So in the first case, when the magnitude of the A beta reaches the 1, at that time, the phase is equal to minus 180 degree. And we have seen that at that time, the response of the amplifier will be oscillatory. And here, the frequency of the oscillation will be the frequency at which this condition will get fulfilled. On the other hand, in the second case, this gain crossover frequency is slightly less than the phase crossover frequency. But as you can see, it is less than by the small margin. That means in this case, when the magnitude reaches the 0 dB, at that time, the phase is very close to minus 180 degree. So in this case, the response of the feedback amplifier will be marginally stable. And because of that, the response of the feedback amplifier will be oscillatory. But eventually, these oscillations will die down. So we can understand it more clearly when we apply the step response to the feedback amplifier. Because if you see the step signal input, then it consists of all sort of frequencies. So from the step response, we can identify how the feedback amplifier will respond over the frequency range. So whenever this gain crossover frequency is same as the phase crossover frequency, and when we apply the step input to this feedback amplifier, then its response will be oscillatory. On the other hand, in the second case, this gain crossover frequency is slightly less than the phase crossover frequency. So in this case, the feedback amplifier is marginally stable, and in this case, when we apply a step input to the feedback amplifier, then its response will look like this. That means initially, we will get some oscillations, but eventually, these oscillations will die down. So for a better stability, we want that this gain crossover frequency should be less than the phase crossover frequency, and at the same time they should not be very close to each other. So this is the third case where this omega GC is less than the omega PC and both are apart from each other. So in this case, when we apply a step input, then this is how the response will look like. And as you can see, it is the response of the more stable system. That means whenever this gain crossover frequency is less than the phase crossover frequency, and as they are apart from each other, then the response of the feedback amplifier will be more stable. So the stability of the feedback amplifier is typically measured in terms of the phase margin. So basically, the phase margin is the difference between the minus 180 degree and the phase at which this gain crosses the 0 dB line. So as we know, at the phase crossover frequency, the phase is equal to minus 180 degree. And let's say at this gain crossover frequency, the phase is equal to phi. So the difference between these two phases is known as the phase margin. Or we can say that this phase margin is equal to phi plus 180 degree. So for example, for a sum feedback amplifier, if the phase at the gain crossover frequency is equal to minus 135 degree, then we can say that the phase margin is equal to 45 degree. So the higher phase margin indicates the better stability of the feedback amplifier. So for the well optimized designs, this phase margin should be at least around 60 degree. So now let us see, for some feedback amplifier, if the phase margin is lower or not in the acceptable range, then how to improve the phase margin. So let's say for a sum feedback amplifier, this is the magnitude response of the mode plot. So similarly, now let us see the phase response. So we have seen that up to 0.1 omega p1, the phase will be almost 0. So then after, it will start increasing and it will reach to the minus 90 degree at the 10 omega p1. That means at the omega p1, the phase will be equal to minus 45 degree. And at the 10 omega p1, it will be around minus 90 degree. So now, the second pole will arrive at the omega p2. So due to the second pole, once again, the phase will start reducing and it will reach to the minus 180 degree at the 10 omega p2. So at the omega p2, it will be equal to minus 135 degree. So once again, due to the third pole, from the point omega p3 onwards, the phase will start reducing and it will be close to the minus 270 degree at the 10 omega p3. So at the omega p3 if we see, then the phase will be close to minus 225 degree. And around 10 times omega p3, the phase will be close to minus 270 degree. So from the given magnitude plot, this is how the phase plot will look like. So clearly as you can see, here the gain crossover frequency is more than the phase crossover frequency. And because of that, the given feedback amplifier is the unstable. So here, one way of improving the response is by reducing the feedback factor. So here in this A beta, if we reduce the value of the beta, or in other words, if we reduce the feedback factor, then this 20 log A beta will reduce. And in this case, if we see the magnitude response, then it will look like this. So as you can see, here since we have reduced the beta, so the entire plot has been shifted downwards. And now, this is the new gain crossover frequency. So here, since we have reduced the beta by this factor, so the gain crossover frequency will shift it towards the left hand side. But here, since the beta is independent of the frequency, so it won't affect the phase plot, and the phase plot will remain the same. So now if we see, then this gain crossover frequency is less than the phase crossover frequency. And now, with the reduced value of the beta, the response of the feedback amplifier will be stable. So here, since we are reducing the beta, so this 20 log A beta plot is reducing. But if we see the closed loop gain, then it will actually increase. For example, let's say at some frequency omega, this open loop gain A is equal to 100 and this beta is equal to 0.1. So in that case, if we see the closed loop gain, then that is roughly equal to 9. But now, if the beta is reduced by the factor of 10, then the closed loop gain will become 50. That means with the reduction in the beta, although this 20 log A beta plot is reducing, but overall if we see, then the closed loop gain will increase. Moreover, with the reducing the beta, although we can improve the stability and we can improve the phase margin to some extent, but at the same time, we are also reducing the amount of feedback in the circuit, and hence we will not get the benefit of the negative feedback that we have discussed earlier, and to some extent we have to compromise those benefits. So the better way of improving the phase margin is by using the frequency compensation. So in this case, the position of the dominant pole in the feedback amplifier is shifted. So for example, let's say this is the magnitude response of the A beta for the sum feedback amplifier, and this is the corresponding phase response. So here, this is the gain crossover frequency, and this will be the phase crossover frequency. And as you can see, here the gain crossover frequency is more than the phase crossover frequency. It means that the feedback amplifier with the given response is unstable. So here, somehow, by shifting the dominant pole towards the origin, it is possible to move the gain crossover frequency towards the left, and in this way, it is possible to get more stable response, and it is possible to improve the phase margin. So as you can see, the first pole is arising at the omega p1. So now, if we shift this dominant pole to the new frequency omega p1 dash, then this is how the new response will look like. That means up to the omega p1 dash, we will have the flat response. And then after, due to the first pole, this magnitude will start reducing at the rate of 20 dB per decade. And it will continue to reduce until the second pole. So as you can see, in this new case, the second pole will arrive at the omega p2. So from this point onward, this magnitude plot will reduce at the rate of 40 dB per decade. And later on, at the omega p3, it will reduce at the 60 dB per decade. But here, the magnitude response only for the two poles is shown. So now if you see, then this magnitude plot will cross the 0 dB line little earlier. Or in other words, now this gain crossover frequency has been shifted towards the left hand side. So now, with the change in the position of this dominant pole, the phase curve will also change. So now, let us see the corresponding phase plot. So here, since the first pole is arising very close to origin, so we can approximate that from the starting itself, the phase will start reducing, and it will reach to the minus 45 degree at this omega p1 dash, and around 10 omega p1 dash, it will be close to minus 90 degree, and then this plot will remain as it is until the 0.1 omega p2, and after that once again it will start reducing, and around 10 omega p2 it will be close to minus 180 degree, and then from the point omega p3 onwards once again it will start reducing, and at around 10 omega p3 it will become minus 270 degree. So in this way, because of the shift in the dominant pole, this is how the new phase plot will look like. So here, now this is the phase crossover frequency, and as you can see, now with the shift in the dominant pole, now this gain crossover frequency is slightly less than the phase crossover frequency, and hence now the response of the feedback amplifier will be stable. Well, how stable? That depends on the phase margin. So in this case, as you can see, this difference is minimal. So this difference can be further improved by shifting the dominant pole towards the origin. So in the second case, as you can see, now this dominant pole is very close to origin. So in this case now if you see, then this gain crossover frequency will arise before the second pole itself. And in this case, now we have the sufficient phase margin. So we can say that for the sufficient phase margin, this gain crossover frequency must occur before the second pole. So if this gain crossover frequency occurs before the second pole, then it is possible to get the desired phase margin, and hence we can also ensure the desired stability in the feedback amplifier. So now the question is, to get the desired phase margin, how to find the location of the required dominant pole? So it can be found from the Bode plot itself. So let's say this is the Bode plot of some feedback amplifier, And as you can see, here this is the gain crossover frequency. So similarly, if we see the phase plot, then this is how it will look like. And here, this is the corresponding phase crossover frequency. So as you can see, since the gain crossover frequency comes after the phase crossover frequency, so the response of the feedback amplifier will be unstable. So let's say, using the frequency compensation, we want to improve the stability. And not only that, we also want the desired phase margin. So for that, now let us find out the required location of the dominant pole. So let's say, for this given feedback amplifier, this is the required phase margin. That means with the frequency compensation at the gain crossover frequency, this should be the phase. So now, to find the desired location of the dominant pole, from this point onward, let us draw a straight line towards the magnitude plot. So on the magnitude plot, where it intersects, from that point onwards, we will draw a line at a 20 dB per decade towards the vertical axis. So now, when we draw this line, then this line will intersect with the original plot at some point. So now, the frequency at this intersection point shows the new location of the dominant pole. That means to get this desired phase margin, the new dominant pole in the feedback amplifier should be located over here. So in this way, by shifting the dominant pole, it is possible to improve the phase margin of the feedback amplifier. And in this way, it is possible to improve the stability. So of course by doing so, it is possible to improve the stability. But at the same time if we see, then now at the low frequencies, we have a much lesser gain. That means now, the response of the feedback amplifier will be sluggish. Or in other words, the bandwidth of the feedback amplifier will get compromised. So in the actual circuits of the feedback amplifier, this dominant pole location is shifted by adding the compensation capacitor at the suitable location in the circuit. But in this video, we will not discuss that part. So I hope in this video, you understood what is phase margin and how to improve the phase margin of the feedback amplifier using the different techniques. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.